of CPUs, but from the other service, if you are not able to limit the number of CPUs to avoid that the same CPU is used by SQL Server and the other service, there is, I think, it is not very beneficial. Yeah, you only limit SQL Server in the use of the number of CPUs. That's it. The other problem is, and again, I'm not going to present this because it's not an easy topic, but normally a so-called scheduler will never ever move to another CPU, and we will see a scheduler later on. Yeah, so let's for the moment think about a scheduler like a logical core. Yeah, so once the scheduler is assigned to a specific CPU, it will never ever move once you enable processor affinity with a specific trace flag. So we will see, I think the trace flag is 8001 or 8002. This is something we will see later in the presentation, but this is definitely something you should consider. So whenever you think it is a good idea to set the process affinity mask, and ensure that you also set the right trace flag in order to allow SQL Server to move the schedulers between the cores. Yeah? So again, I'm not going to present this, but at least these two things are very important. Yeah? So that's it from a processor affinity mask. So the next thing, in order to allow SQL Server to run queries in Parallelism, that your maximum degree of parallelism must be set to 0 or anything else which is greater than 1. So again, from a GUI perspective, when I open the server settings, so you can see the cost threshold for parallelism is set to 5 and the maximum degree of parallelism is set to 0. And this is exactly what I'm talking about. Whenever you set maximum degree of parallelism to 0 or anything else which is not 1, you allow SQL Server to use more than one core. Yeah? So this is definitely a pre-requirement. So, and by the way, I'm currently working with a customer on a system, on an SAP system, which is running on SAP. And SAP recommends to set a maximum degree of parallelism to 1, which means every query, every user query is single-threaded. Internally, SAP run all their queries with a hint which is maxDOB, which overrides the instance setting. So, and I think this is a little bit unfair because SAP, the internal processes are running very fast. All user requests are running really, really slow because of missing parallelism. Okay, so there's another pre-requirement which is related to the resource governor. So a resource governor is something I think we have time, I'm pretty sure we have time, so that I can present the behavior and the functionality of the resource governor. But overall, on a resource pool, you can set the maximum degree of parallelism, which allows you, I would say, more control about specific connections. So for example, you want to make sure that a specific connection can run queries with a max stop of 8 or whatever, but you want to avoid that other connections at the same time running queries in parallel with the same maximum degree of parallelism, maybe just 2. This is definitely possible by just using or configure the resource governor. Yeah. So this is a very, very nice and a very great feature, which is only available in the enterprise version for good reasons. But it will give you much more control about maximum degree of parallelism and for sure other settings related to a specific connection. And the last one, for sure, is the estimated costs to run a serial plan for a query is higher than the value set in a cost threshold for parallelism. Again, this is a second setting on an instance level, which is cost threshold for parallelism, which is by default still 5. Yeah, so we had a discussion with Microsoft about it, and why not setting maximum degree of parallelism? Why not setting cost threshold for parallelism to something else like 5? The problem is there is no best guess. So even if Microsoft with a new version, I don't know, SQL Server 2021 or whatever, will increase the cost threshold for parallelism to, I don't know, 50 or whatever, because 5 is a very, very old value with very, very slow CPUs. CPU, the power of CPU, the speed of the CPU increases over time. And that is the reason why I guess 5 is not the recommended value anymore. But is 50 correct? Is 100 correct? No one really knows, because it depends on your workload. So, and therefore Microsoft decided to leave it as it is. So that means it is still 5. But definitely this is something you should configure, or you should rearrange whenever you know the workload of your SQL Server. Okay, cool. Yes, so I will give you a few examples. First of all, there is one DMV which you can use, which is this Dmos, this info. And apart from the 3 columns, you have much more columns. But with regards to parallelism, we have 3 information, or we have 2, because this is calculated. We have 2 columns which will already give you the information you need. So you can see I have 8 logical CPUs, hyper-thread ratio of 8. That means I have only 1 core on my machine, 1 physical CPU on my machine. So this is definitely something you should know before you configure, or maybe even start performance tuning, because it has a big impact. Okay, so the processor affinity I already explained. I would like to skip this because again, it will take time just to explain how it works. So therefore, I want to go to maximum degree of parallelism. So let me execute a query. And before I'm executing the query, I want to ensure that cost ratio for parallelism is set to 5 and maximum degree of parallelism is set to 0. That means SQL Server can run queries in parallel whenever your cost threshold, your estimated costs are bigger than 5. Perfect. So you, for sure, just to make sure that everything is running, I can double check. Maximum degree of parallelism is set to 0. Max stop on database level is also set to 0. And when I now execute this query, it's a very easy one. I'm just counting the records. You can see I got a plan. So the plan is running in parallel. You can see parallelism here. So parallelism starts here. Honestly, it starts here. So there's something which is called a so-called page supplier, which is not visible in the query execution plan. But it ensures that the table scan gets a specific portion of pages for every thread. But here from a query execution plan, you can see whenever you have the double arrow, this identifies that the operator or the iterator is running in parallel. So parallelism stops here. So not the entire plan, not the entire query is running in parallel, just half of it. So in the end, we will always end up with a so-called gather stream, that one, because all the threads have all the pages from the threads, they have to combine. And once all the pages or all the rows are combined, then this operator will pass all the rows to the next operator in a serial manner. So that's it. Good. The interesting information you can see on the select operator. So we can see that the degree of parallelism is set is 8. That means the query is currently running was executed with 8 concurrent threads. You can see the estimated subtree cost, which is 2.7, which is less than 5. But when we run the query just with 1 thread, we will see it costs more than 5. That is a reason why SQL Server decided to execute this query in parallel. So when I now, and this is exactly the other way around, when you now change the maximum degree of parallelism to 1 to limit the number of threads which can be allocated by a specific query, and you run the same query again, you will see this is a complete different plan. We still have a table scan, we have a hash match this time, and we do not have any kind of parallelism. There is no parallelism. We can see it here also from a select operator information. Degree of parallelism is set to 0, and the costs are almost 7. And again, that was a reason why SQL Server decided to run the query in parallel with the other configuration, where I allowed SQL Server to run queries in parallel. Yeah? So the cost, the estimated costs, are higher than the cost threshold for parallelism. There is another information. Sometimes you wonder why your query is not running in parallel, and you can see a property named non-parallel plan reason, which is always there when the query has a potential to run in parallel. And this time you can see the setting or the information max dop set to 1. That means the query was limited, not the but the query won't run in parallel. Yeah? So that's it. Sometimes this is really helpful to understand why your query is not running in parallel. So, so we decided here, we decided to set the maximum degree of parallelism to 1 on an instance level. But again, on a query level, I still have a chance to override the setting. So with the query hint max drop 0, you can see once I hint the query to run the query in parallel, the instance setting and also the database setting is completely overwritten. It is completely ignored. That sometimes makes sense because, again, you can set on an instance level the maximum degree of parallelism to 1 or to 2 or whatever. But for specific queries where it really makes sense to allocate more than 1 or 2 CPUs, you can hint the query and ensure that you get the best performance. Yeah, that is definitely something I would recommend. Yeah? Really thinking about when it makes sense to run queries in parallel. Because as we will see in a moment, in an OLTP systems, a lot of queries are running slower when they are running in parallel. Okay. So now I set, this is something I want to skip. I just want to tell you that on a database level, you also have the chance to set the maximum degree of parallelism. You can see it here, max dop, on a database level. That means on an instance level, you can set the value. On a database level, you can set a value which overrides the instance value for the specific database. And you can hint the query to use more or less threads by max dop, whatever. So this will again override the database setting, and this will override the instance setting. Yeah. I just want to do some housekeeping because otherwise everything else is not working anymore. Okay, I will go to the resource governor later on because it takes some time and I want to ensure that I will present other things before. Okay, so the cost threshold for parallelism. So we set the cost threshold for parallelism to 5, which is the default, just to ensure that everything is working, and I just need to check it. Perfect. So this is a query very similar to the other query, and we can see that the cost threshold for parallelism is set to 5, and the estimated subquery costs, you can see it here, is something about 7. It's exactly the same query as before. So when I hint the query just to use one thread. This is the base. This is what SQL Server internally use once it goes into the so-called execution or optimization phases. So we have 3 optimization phases, 0, 1, and 2. And in optimization phase 0, SQL Server estimated the costs. And when the cost is higher than a specific threshold, SQL Server will execute the next execution phase, which is 1. And here, this is the first time where SQL Server considers running the query in parallel. And again, this is not a guarantee, because there are several operators, like a top operator, for example, which cannot be even executed in parallel. That means some queries, even if the costs of the estimated costs are much bigger than the cost threshold for parallelism set on an instance level, they cannot be executed in parallel because of the algorithm of the operator. Yeah, a top operator, again, is a good example. Whenever you use a top operator, SQL Server cannot run the query in parallel. So do not wonder when some queries, which are very expensive, cannot run or will never ever run in parallel. There is no chance to do it. So, and now I will give SQL Server the chance to consider parallelism. And you can see, because of the estimated subtree costs, which were 7, now it reduced the estimated subtree costs to, I don't know, 3 by introducing parallelism. That is the way it works. Just to understand what kind of settings will influence or impact the parallelism. So sometimes it is very useful to understand why a specific query, or the other way around. You want to force a specific query to run in parallel to see, I don't know, the cost reduction, and not even the cost reduction, also the elapsed time, because in the end, I personally do not care about costs, because costs are always estimated. So that means costs, and you already see this in the execution plan. There is nothing like the actual cost. There's always something named estimated subtree cost. And an estimation, a cost estimation, this is based on cardinality. That means SQL Server tries to estimate the number of rows which are going through the pipeline, which SQL Server have to process, right? The problem here for sure is when your cardinality estimation, so the statistics are stale, so they are not accurate. That means that SQL Server will calculate and suggest a plan, because we always need to have a plan, but the plan is maybe far away from the best plan, because again, the cardinality estimation maybe is completely wrong. So that means when you rely on estimated subtree costs, this shouldn't be the indicator that a query execution plan is a good or bad one. What definitely is more important is this is the CPU time, because CPU time in the end matters, and for sure also the elapsed time. But we will see this in a minute, that the elapsed time is nothing else than wait time plus CPU time. That means even the elapsed time is nothing you should worry about it for sure, but you cannot directly, it's the other way around. There are a lot of other factors, like a lock, like, I don't know, we have more than 1,000 specific wait types. So that means your query can wait for on more than 1,000 resources. That means sometimes you have a query which is running horrible slow, but the reason that the query is running slow is not because of this query. It is because of another query which maybe block a specific resource. Yeah. So therefore, never ever rely on costs. But from a Microsoft internal perspective, there's nothing else to rely on as on estimated subtree costs, because SQL Server do not know the actual cost before executing the query, right? And that is the reason why you have to be very careful with parallelism. Parallelism, again, is dependent on subtree costs, but subtree costs are based on cardinality estimation. So when your statistics are stale, the costs are completely wrong, and therefore the choice, running the query in parallel, might be also wrong. Okay. Again, sometimes I want to see how a query looks like from an execution plan when it runs in parallel. So you can see this is the estimated subquery cost, which is almost 2. It is running in serial because of this. And now I execute the same query with a query trace on, a query trace flag 8649. So this time we can see the same query is running in parallel. You can see degree of parallelism is 8, and the estimated subquery cost is something about 1.3858, which is almost same. You can see there's, I would say the cost reduction is definitely neglectable. It is not worth to allocate 8 threads, yeah, for the same query just to save 0.5 costs. Yeah. It's definitely nothing you should worry about it. I think in SQL Server 2016 there's a hint introduced called Enable Parallel Plan Reference, which you can use instead of the query trace flag. It's exactly, it behaves the same. So you can see the query is running in parallel. Yeah. It is your choice. Either you can use query trace on 8649, or you can use enable parallel plan reference. Yeah. Just to see and understand what does it mean when I force SQL Server to run the query in parallel in terms of elapsed time, in terms of costs, in terms of CPU. Yeah. Sometimes it's definitely helpful. Okay, I will switch this part. Okay, now it becomes a little bit more complicated. So hopefully you are familiar with NUMA nodes. Yeah? So I will try to explain NUMA nodes in a few sentences. So the new CPU architecture is NUMA. Before it was UMA. Yeah? So NUMA means that we have one physical core, one physical CPU, and within one physical CPU, in my case, we have 8 logical cores. So now let's consider we have another physical core with another 8 logical cores. That means I have 2 physical cores with 16 logical cores. The problem is that whenever you need to exchange data between one physical core and the other physical core, which is called a NUMA, consider a NUMA like a physical core. So when you need to exchange data between NUMA nodes, then there is a latency. Because internally, within the same NUMA, all logical cores can use the internal cache. Yeah? There are a lot of caches available, and in order to exchange data, it is just memory which is directly allocated and close to the CPU. This is definitely the fastest way to exchange data. But now let's consider the following. I allow SQL Server to run a query on 16 cores. That means I'm not allocating only one NUMA node and benefit from the internal caches, but I will tell SQL Server also to use the other NUMA node. Now SQL Server is in trouble because SQL Server must exchange data between one NUMA node and the other NUMA node. And this has a latency because there is nothing like a cache which can be used. It is called a bus. And the bus is so much slower. And that is a reason why you always have to ensure that you follow the recommendation from Microsoft. Let me open the recommendation, the latest recommendation from Microsoft. So you can see SQL Server 2016 plus and SQL Server 2014 and older versions. So the recommendation is, and there's one difference here. Yeah? So anything else stays the same. So if you have less than or equal to 8 logical processor, the guidance is keep max stop at or below the number of logical processors. That means when I have a NUMA node, which have 8 logical cores, I should keep maxstop to the number of logical nodes or logical cores within one NUMA node, but at maximum 8. You can see how it works. Yeah? The only difference is when you have more than 16 logical processors per NUMA node. Yeah? In SQL Server 16 and newer, it means keep maxstop at half of the number of logical processors per NUMA node with a maximum of 16. In older version, when you have more than 8 logical processors per NUMA node, keep maxstop at 8. And you can see that SQL Server 2016 and 19 is now able to allocate more cores within one NUMA because, again, the number of records, the complexity of queries is growing over time. And that is the reason why SQL Server changed the, I would say, the internal architecture. Now SQL Server can allocate more than 8 cores, which sometimes can give you a great performance benefit. Again, sometimes it is exactly the other way around, but at least SQL Server have a chance to allocate more than 8 cores. It can allocate 16 cores. Okay. So the NUMA nodes, for sure, you can see in the GUI. You can see it in this Dmos nodes. We can see we have 2 nodes, but this doesn't mean I have 2 NUMA nodes, because node 64 is a so-called DAC, the dedicated admin connection. There has to be 1 node in any case, because otherwise SQL Server cannot guarantee that you can access SQL Server even when SQL Server is not accessible by a normal user connection. That is a reason why we need to have 1 logical node for the so-called DAC connection. Great. So there is also something which is related to NUMA, which is Dmos memory nodes, and this is more important, Dmos memory clerks. Let me execute this one. What you can see is we have 270 rows. That means we have 270 memory clerks available. And these are all the memory clerks. What you also have to understand is that, let me go here. We can see that every memory clerk is bound to a specific node. And the node is nothing else than the NUMA node. That means when you have more than 1 node, NUMA node on your machine, you will double the number of memory clerks, because 1 memory clerk is allocated to a specific NUMA node and not the same memory clerk. But again, it is the same memory clerk, but for sure it is another memory address. This is bound to the other NUMA node. That means here you already get an idea which kind of data can be exchanged between NUMA nodes. For example, the pages. The pages are related and bound to a specific NUMA node. And now again, consider that you have something like a table scan, and the table scan will scan pages, I don't know, millions of pages across 2 NUMA nodes. That means SQL Server need to exchange data between the NUMA nodes, which can take much, much more time. There's one specific tool which you can use. Let me go down here. It is OS Stress. Here, OS Stress. This is something which you can, OS Stress, core.info.exe, which you can use in order to see the latency between NUMA nodes. And you can see this is not my machine, because my machine only have 1 NUMA node. This is an example from a VM which I have created. So this is the latency. This is NUMA node 0 to NUMA node 0. This is the internal cache. Honestly, I guess this is a bug. It should be 1 as well, because NUMA node 1 to NUMA node 1 means we are using the cache. There is no latency. But when I now want to exchange data between NUMA node 1 and NUMA node 0, we can see we have a latency of 20, we have a latency of 30%. In terms of the CPU power, that means you reduce already the performance of the query by 30%, just by allowing SQL Server to exchange data between the NUMA nodes. This is something you should avoid, because there is definitely a big overhead related to cross-NUMA node data exchange, right? So I have one example here to give you an impression what it means to execute a query in parallel, to execute a query in serial, and when we run it in parallel, what it means to run a query with 2, 3, 4, 5, 6, 7, and 8 threads. Okay, so this is just the query I used. So a very easy query. And when I execute the query, so you can see it takes a moment, but at least let me do this. I just need to include the estimated execution plan. You can see by default, SQL Server will run this query in parallel. And what I have done, I limited the number of threads by max stop 1, 2, 3, 4, and so forth. And this is a result. And this is very interesting. Again, it is always the same query. You can see here on the x-axis, we have the degree of parallelism, so the number of threads SQL Server can use, 1, 2, 3, and so forth, and the time it takes. And the time is nothing else than the elapsed time, and the elapsed time is nothing else than CPU time plus wait time. You can see on the right-hand side the wait time, because the only wait time we can monitor is the so-called CX package, class exchange packet, or the CX consumer, class exchange consumer. This was introduced, I think, in 2016 or 17. Yeah? So this will give you an impression that whenever you execute the query just with one thread, we can see the average or the CPU time is 31 and the elapsed time is 45. When we compare this and we compare this with the maximum degree of parallelism 8, you can see the CPU time it takes is now 2.5 seconds and the elapsed time is 1 second. That means this query is definitely running much, much slower the more threads you allocate to the query. And now you wonder why. The problem is not about anything. This is not the query is not specific. The problem why it takes longer is the CX packet, because CX packet is a wait type which tells you how long it takes to run the query in parallel. So let me go back to the query. So you can see the query itself starts with 2 threads, which can run in parallel because merge is not a blocking operator. So we have one thread or one branch here, and the branch can allocate 8 threads in parallel. This is something which we can see here as well. So thread stats, we have 3 branches, yeah, but we can see that the query itself is only running with 8 threads. Okay, so this has to be coordinated. So you from a complexity, you can already imagine what it means when the branches are running in parallel on different threads. This has to be coordinated. And the time it takes from the first operator, which is running in parallel, this one, and the last operator, which is the gather stream, this is the time which is measured in the CX packet. So CX packet, per definition, is nothing else than the time for parallelism. There's nothing bad, there's nothing wrong, because people always ask me, okay, I have a lot of CX packet, is this good or is this bad? It depends. CXPacket only tells you that you run queries in parallel. And the higher the number of CXPacket is in comparison to all other weight stats, the more prominent it gets, and the more it will tell you that your queries are running in parallel, because they are more expensive than your cost threshold of parallelism. And I hope now you understand what it means, because the query is more expensive than 5. It costs, what is it? Yeah, you can see the estimated subtree cost, which is, I don't know, 70 million or whatever, 7 million, which is definitely more than your cost threshold for parallelism, which is set to 5, I guess, at the moment. So again, when you see the high number of CXPacket wait time, this is nothing you should worry about. The only indication it will give you is that your queries are running in parallel because your cost threshold for parallelism is either too less, or your queries are too expensive. So this can give you a hint that you are missing indexes, that you are missing, I don't know, or you have complex queries, which you can rewrite in order to reduce the cost of a query. And when you reduce the cost, and you fall underneath the cost threshold for parallelism, SQL Server now will execute the same query, not in parallel, but with one thread only. So this is about CXPacket, and you can see the time it takes to coordinate all the threads. It is increasing over time. The more DOP we have, the more we have to wait. And that is the reason why the elapsed time is increasing, right? And this is something you should worry about, because this is a very good example. We can see we are waiting the elapsed time. This is user experience. This is 1 second comparing to 30, 31, 40, 45 milliseconds. This is a big difference, right? The same query. Okay, let me go down. I'm running a little bit out of time. Just want to make sure that this is working. So let us again talk a little bit about CXPacket. So I will give you an example. Maybe we can start with an example here. So the server have a so-called maximum worker count. And the maximum worker count will tell SQL Server how many worker threads are available on SQL Server. So there's a formula which you can use, and SQL Server internal use, which is dependent on the architecture, which is dependent on memory, and I think it's also dependent on CPU. That means the more CPUs you have, the more worker threads you can run in parallel. So currently I limited my system, you can see it here, to 128. Normally it should be 576. But I do not want to run that much queries in parallel for the example which I'm going to show. Instead, I will lower the maximum worker threads. Yeah? So I can either do this or the other way around. The effect or the impact is the same. So when I execute this query, this is a serial plan for sure, because I have an option max stop 1. So when I now execute the same query, either in a serial way, or when I run it like this, you can see the same query now is running in parallel, because the cost estimated subtree costs are much higher than the configured 5. So we can run the same query in 2 different ways. So let me execute this. First of all, I want to open CMD. Come on, why does it? Okay, good. Great. So OStress is a tool which you can download for free. I connect to my SQL Server. to the database, AdventureWorks 2017, and run this query on 10 times on 300 threads in parallel. Okay? This is more than the configured 128 threads. Because you can imagine when I execute this query, I only allocate one thread because it's running in parallel, not in parallel, it's running serial. But if I now execute more than 128 queries at the same time, 300 times, we allocate, or we want to allocate, more threads than we currently have because we only have 128. Let me execute this one.
Thorsten?
Yeah.
10 minutes left for you.
Yeah. Yeah. So what we can see here, and it takes a moment, this is nothing I should worry about, is we can use this Dmos schedulers, and we can use this Dmos waiting task. Let me see whether I can execute the query. You can see that my entire system is horrible slow, and we already can see here in the background, yeah, error messages. So, and you can see nothing is working anymore. So I need to stop MD here. Now it's back. Okay, I cannot see the waiting task anymore because waiting task will only give you information about the current running queries, which is not the case anymore because I completely stopped the overhead, but I can run the query another time. But important is that from a Dmos scheduler, this was a query which I use, this Dmos scheduler, we have a few columns. So first of all, the scheduler, and the scheduler is nothing else than the NUMA ID. There's NUMA, so we have 8 logical cores within my NUMA. This is a current task count. So these are the tasks which are currently looking for a thread within the scheduler. So these are the current or the runnable task count. That means we can already see that there are more threads, more tasks waiting for a free thread. You can see that in the end, there's one column called work queue count. And the work queue count, this is a queue. That means the task is nothing else than the query must wait for a free thread. And the thread is not available because there is only a limited number of threads available in every system, right? So therefore, this task have to wait for the thread. And this is a queue. And the queue will definitely, it's increasing over time. The more queries you're running in parallel, and the more it is increasing, the longer it takes for the last query to be executed. And this is something which is called a thread pool starvation. Maybe I can execute the same, maybe it works. Why is CMD? CMD. Sorry. I will execute again another time. And hopefully this is Dmos waiting task this time. So I need to execute the same query again. Maybe we can see it even from a waiting time. Dmos waiting task. Oh, let's hope it works. Yes, cool. I will stop here. So this is Dmos waiting task. It will give you information about the current request and the related wait time. And what you can see here is that we had, this is just a snapshot, right? It's just a snapshot. We had 9 queries waiting for an idle thread. And you can see they are waiting. This query is already waiting 128 milliseconds just for an idle thread. It means this is a task waiting for the CPU. And because of this, it has to wait until a thread becomes idle. Therefore, the elapsed time is increasing over time, not the CPU time, because the CPU time at that moment is still 0. That means when you now try to tune a workload like this, you have a high elapsed time, but less CPU time. And the problem is that the difference between the elapsed time and the CPU time is wait time. And now you need to figure out why and for which resource this specific query is waiting for. And you can do this with Dmos waiting task. You have Dmos wait stats. You have query store available. You have a lot of options in order to try to figure out why this query is running that slow. And here, this is thread pool starvation, right? And this is something you can handle only by either making sure that you are not running that much queries in parallel, or you will increase the maximum worker count by giving or by allocating more CPUs to a VM, for example, or when you are in Azure or whatever, you can easily increase the resources, which is in this case vCores. Yeah, when you have more vCores, you get more worker threads. When you have more worker threads, yeah, it is less likely that you're running in a thread pool starvation, right? And now consider the following: you're running the same query, not with max.1. I do not want to do this because you already, hopefully you understand the impact already. So this time the query will even allocate 8 threads because it is not just limited to 1 thread. So therefore you have 8 times the number of threads allocated by the same amount of requests. So that means executing the same queries on 300 parallel threads. That means you are not ending up with 300, you are ending up with 8 times 300 threads. So therefore your thread starvation has even a much bigger impact, and all or more queries have to wait longer so that they can even start to be executed from a CPU perspective. So this is called thread pool starvation. And believe me, when you have this high CX packet and you have high thread pool starvation, then you have a problem with parallelism. Otherwise, you do not have a problem with parallelism. Yeah, so there's another one which is related to page latches, but this is nothing I want to cover here. But keep this in mind: CX packet, when you have a high number of CX packet, it only tells you that your queries are expensive. When you also see thread pool as a wait time, then you are in trouble because now you have a hardware or a resource problem, which is really, really hard to solve. Okay, that's about parallelism. Any question?
No question so far, Torsten.
Okay.
I think it was a very amazing session, a wow session, you know.
Thanks.
So it was very clear.
Cool.
I will wait maybe one minute to see if some question rise on the chat. Okay, so it was a very nice session. It was a big pleasure to having you to the session, Torsten. Thank you for your session. It was very great. Ok. Des questions jusqu'ici? Non, pas de questions? Non, donc du coup, ce que je vais faire, c'est que je vais arrêter. I will stop the recording now.